Welcome, everyone. I would like to thank you for coming to my talk and the organizers for the opportunity to speak to you. It's my pleasure and a privilege. My name is Oksana Riba Grognuz. I'm a senior data science engineer at the Swiss Data Science Center, and I'm delighted to share with you how our collaborative platform Renku helps to address the challenges of reproducibility in data science. In my talk, I will explain what is Renku and why it is different from other platforms. I will then share with you how Renku can help and where we can find it. So, what is Renku about? Renku is a knowledge infrastructure that accompanies a scientist throughout all stages of research lifecycle. Knowledge graph at its core connects all other components and links version digital objects within and across collaborative projects. Starting from the project planning stage, we can leverage the Renku knowledge graph to plan data management, to identify existing research and data that are useful for the project at hand, to evaluate the required effort. Next, at data preparation stage, we can enable transparency and reproducibility by bringing data to versioned Renku containers linked to the data source, where Renku will automatically track changes in data contents and properties. To explore the data, we can use any of Renku flavors for interactive sessions and use custom templates to automate and standardize preprocessing steps for all collaborators. Then, rather than putting an extra effort to ensure the reproducibility of the final solution, we can leverage automatic provenance tracking for every model that we build on Renku. We can also extract and register machine learning model properties using Renku plugins, such as Renku MLS. Version control is vital in reproducibility, since it helps track changes we or our collaborators make to projects' code and documentation. Versioning ensures that every contributor has access to the latest validated code. Codes, with all their dependencies, are packaged in self-contained versioned containers that make Renku projects portable and reproducible across different systems and infrastructures. Finally, by activating automatic tracking, we can transform our commands to workflow templates that can be shared and reused on a different context and with different parameter settings. All the steps that I mentioned on previous slides are easy on Renku. Each of us has own preferences and favorite tools. With Renku, we can achieve full computational reproducibility using tool stack of our choice. We can manipulate datasets and work on Renku projects in web app or from command line. We can build the environment from the existing flavors of interactive sessions, such as Jupyter Lab, RStudio, VS Code, or Virtual Desktop, or create our own flavor with desired dependencies, annotated metadata, and pre-configured automation. When we create a new Renku project, we simply select the desired template from the list of maintained Docker images with different flavors of Renku interactive sessions. Renku will monitor template status and inform us when the new versions become available. Updating our project to a new template is as easy as single click in Renku web app without overhead for local support and operations. Renku web user interface is one of the ways to explore the existing projects on Renku, reuse them, or create new ones. In this interface, we can navigate the projects, their knowledge graph with provenance information, and collaborate on our projects. We can also switch to GitLab to edit code in GitLab Web IDE or use GitLab CI for automation within or across projects. In a nutshell, Renku consists of 3 clients coupled to a range of supporting services with custom microservices providing the glue. In the top panel, we see the clients consisting of web user interface, interactive sessions, and command line interface that connect to supporting services using Renku Core, Notebook Service, Knowledge Graph, and API Gateway. These supporting services consist of GitLab for Renku project repository management, Jupyter Hub for interactive session management, Keycloak for authentication, Graph Database Jena to store the Renku knowledge graph, and PostgreSQL relational database for GitLab, Jupyter Hub, and Keycloak. Server components are deployed on a Kubernetes cluster on the top of OpenStack switch engines for virtual machines, storage, and network. And there is no vendor or technology lock-in for the user, except for Docker and Git, which are here to stay for a while. Why is Renku different from other collaborative platforms? Renku is a feature-rich platform providing command line interface, platform, and a service for community as outlined on the x-axis that supports users for code and data versioning, environment containerization, and workflow execution shown on the y-axis. There are other platforms that cover the same range of features, such as CodeOcean, Pachyderm, Terra, or Wholetail. The uniqueness of Renku relates to its knowledge graph that connects versioned digital objects, tracked provenance, and workflow execution. Users populate the knowledge graph through their actions by creating datasets and annotating them with keywords, by constructing workflows, by using domain-specific plugins that can extend the basic metadata model for specific uses. Renku Knowledge Graph creates an ecosystem with linked data not only inside a given project, but also across projects and even Renku instances. Two Renku knowledge graphs can be simply joined together. The knowledge graph is accessible from command line and platform and is actively developed to address the needs of scientific community. This schema illustrates the main idea behind the knowledge graph on the example of interactions use and create shown in violet and pink respectively. This toy graph shows that our collaborator used data annotated with a range of properties such as author, keywords, and format, and a machine learning model indicated with the violet arrows on the left side to create a workflow that generates new data, indicated with a pink left to right arrow in the middle. In our turn, we use this newly generated data and another model in our workflow, two violet arrows on the right. A deeper look at the ontology used in Renku provenance graph reveals its power. Based on open standards, Renku tracks user commands to generate a task template, shown on the left, with a range of properties such as name, description, and keywords, as well as connected templates for inputs, outputs, and command arguments. Renku will track every execution of a given task template, shown on the right, along with respective properties such as agents executing the template, start and end of the run. Task execution is connected to artifacts for inputs, outputs, and parameters, which may be different than default ones recorded as values in task template. Currently, we connect to external domain ontologies at the level of template properties for inputs, outputs, and command arguments. For example, input file can be defined by domain-specific ontology describing the output of a given instrument, and the contents of the file may be described using controlled vocabulary of a given domain. Renku provenance graph is coupled to dataset properties that are captured at three different levels shown in this slide. Renku dataset containers represent a distinct node type with a range of properties such as agents creating the datasets, its source, name, and description. The dataset consists of digital documents tracked for changes and annotated with the respective properties, for example, encoding format and checksum. Renku tracks how datasets are used in different Renku projects. Look at the box on the right, which in turn are also annotated with a range of metadata types and properties. Again, we can connect to domain-specific ontologies and controlled vocabularies through multiple additional types and associated properties. For example, we can annotate digital document containing sample measurements with the dedicated type sample that will have name property based on the controlled vocabulary values to indicate whether it is material an organism or a cell. How can Renku help your research? Most exploratory avenues lead to a dead end. From those that have a result, only a handful will bring enough value to result in a scientific publication. Finding these can take a long time, and here Renku can help by accelerating the fail-try cycle with automated provenance tracking, reusable components, data, and environment versioning. By tracking every exploratory avenue, Renku allows us to reuse bits and pieces of different steps to eliminate failing hypotheses faster and focus on exploratory avenues that create value. Furthermore, once ready with the final solution, we do not need to take any extra steps to ensure its reproducibility. Reusable and reproducible workflows are new standards across many disciplines that rely on data science. However, creation of such workflows often requires mastery of the workflow language. With Renku, we do not need to worry about this, as it captures workflows from our input, allowing us to focus on delivering the best possible data science solution. Renku connects workflows with the metadata for underlying version components, code, data, and environment, thus ensuring that workflows are findable, reusable, and reproducible. For those of us who deliver solutions for highly regulated domains, compliance can be a big burden. With GitLab CI/CD component coupled to Renku Knowledge Graph, we can easily set up a continuous self-assessment against a set of standards and focus on delivering the solution that will be compliant by design. Benchmarking systems are another great case illustrating the advantage of coupling GitLab CI/CD with Renku Knowledge Graph. In this example, I'm showing an implementation of modular and extendable community benchmarking system for computational biology methods on Renku. In many areas of biology, new methods appear so quickly that by the time these are benchmarked, the results are already obsolete. With Renku, we can apply CI/CD principles to community benchmarking by putting in place templates for modular and extensible components for benchmarking datasets, method workflows, and metrics workflows. Each template is pre-configured for automation and annotated with the right metadata to allow for flexible component connection through the knowledge graph. Thus, the format and keywords of the datasets will trigger the application of compatible method workflows through scheduled automated knowledge graph queries. Similarly, methods link to metrics and then to the dashboard. Community of method users can interactively evaluate the methods on different datasets with custom method rankings and pull any of the components that are packaged with dependencies and metadata to be reproduced, reused, and integrated on other platforms. We are a big development team at Renku, sharing a common vision. A vision of a fair ecosystem on Renku, with fair being findable, accessible, interoperable, and reusable. A system with a knowledge graph at its heart, connecting version digital objects with full domain-specific provenance. All components of such ecosystem are flexible modules packaged with all dependencies and metadata to be reproduced, reused, and integrated on other platforms. I will wrap up by sharing where we can find Renku. Renku is provided by the Swiss Data Science Center as PPEX module and is available as open source on GitHub. We also provide a free community service which is available at renkulab.io. To fine-tune Renku to specific needs, we deliver also custom institutional deployments in different flavors, such as software as a service, cloud, or in-house deployments. With these, I would like to thank you for listening, and you are welcome to reach out to Renku community and Renku team at Discourse, at Gitter, or at GitHub, or simply connect with me on LinkedIn and ask any questions that you may have. You can see the barcode on bottom right.